folks. We'll start today with taking questions from this worksheet 3. So if anybody has some questions here from worksheet 3, Henry? Number 2, sure. So the formula that we're using is the continuous growth or decay formula. So in our case, the present value is 20,000. E is that number, 2.7, yada, yada, yada. R is 0.045. And then the T in this case would be 7. So I'll just type that into my calculator and see what we get. So 27,405.19. 405. So there's that. Okay there?
Yes, less than interest to A, right?
Yep.
So B is target.
So B I'm just going to do on my calculator. I'll change my mode real quick. Okay, so I'll have my function is 20,000 e to the 0.045x, and then 50,000. And I'll choose my, so since x is time, stop talking please, ladies. The x min should be 0. It took me 7 years to get to 27,000. So to go to 50,000, what's your guess? Gotta be more than 7 at least, right? 60 sounds reasonable. Again, the window just has to be able to see the intersection, right? A good window, you can see the intersection. Doesn't really matter, but if we think about the problem, usually we can get the intersection one shot. That's really what we're hoping for. The y, well, the minimum value here is the initial investment. And then I have to see 50,000. So I don't know, I'll pick something bigger than 50,000 in the interest of doing a round number. Let's do 100,000. Let's hit graph. So there's my account value curve. And there's my 50,000. So the intersection is what I'm looking for. So I'll press second trace, choose the intersect command, first curve, second curve, guess. So that happens at 20.4 years. So that's my value for B. Okay with that? Really the same, we would do the same thing for 1 as well, right? So in part A, you just plug the number into the model. In part B, you find the intersection between the model and that, the number. Same idea for both 1 and 2. Other questions from this? Harley? Okay. So the only difference here is that instead of giving the time explicitly, we give dates. So if T is the number of years since 1989, and in part B or part A we're talking about 1999, what is T? So I'll just go and do 738 e to the 0.345 times 10. So there I get 23,247. And I rounded that to the whole number since we're talking about termites. Doesn't make sense to talk about a fraction of a termite. In part B, we want to find the year when we got 1,500 termites. So I'm going to do this by graphing. So I'll do 738 e to the 0.3445x. And then we'll do this as 1,500. And then I'll pick a window. So when t was 10, we got way more than 15,000 or 1,500, right? So 0 to 10 seems like a decent guess there. And then for my y's, I don't know, we'll do 0 to, well, we got to do something bigger than 1,500, so maybe 2,000. Just in the interest of using a round number. Like graph. So there's my termites collected. There's 1,500. So second trace, intersect command, enter for first curve, enter for second curve, enter for guess. And it happens 2.06 would be my value for t. So in other words, that's like the same as sometime during 1991. Or early in 1991, right? Is everybody okay with that idea? Harley, you feel good there? Really kind of the same thing as the previous problem, right? Same techniques. Okay. Any other questions from this assignment before we get started on the new stuff for today? Okie dokie. So we're going to continue talking more about logarithms today. Before we get started here, though, I just want to recall our definition. Oops. So if b and y are positive and b is not equal to 1, then we know that log base b of y is equal to x if and only if b to the x is equal to y. So we're going to continue to kind of use this definition today. That's why I wanted to write it down again, just to make sure that we remembered this. Before we get going too much further, though, when we talk about logarithms, I want to introduce a little bit of vocabulary here and talk about how we can use our calculator to evaluate some logarithms. So the first piece of vocab is we're going to use the phrase common logarithm to refer to log base 10. And when we write log base 10, we're not going to write the 10 in that spot. We're just going to write log with no subscript. and understand that when we write log with no subscript, there's really a 10 there. And we've done this a bunch of times in math, right? Oftentimes we'll write just x, and we don't write the coefficient in front of x, but we know in front of x there's a 1. For example, when we write the variable x, we know there's an exponent on that. What is the exponent there? 1, right? When we write the square root symbol, we don't write an index like inside of the little check mark part, even though we know that there's an index there. What number is there that we don't write? 2, right? So we've done this a bunch of times before, where we just understand the value to be something that happens very frequently, and we don't bother to write it in. We just accept that, like, that's what goes there. Everybody feel okay on that? Right? There's a second logarithm that we have a special name for. That's log base e. We call this one the natural logarithm. And the abbreviation for the natural logarithm is ln. So if you see an ln, we're going to understand that to be log base e. Everybody's okay there? Okay, so let's, if you have your graphing calculator with you, I'd invite you to take it out right now. And we'll show you guys how to use your calculator to evaluate some logarithms. So the first thing I'd like you to do is, if you look at the left-hand side of your calculator, about halfway up, you'll see the button that says LOG on it. That is the common logarithm. So for example, if we wanted to take log of 8, we can just press that button, type in the 8, and then close the parentheses, and press enter, and the calculator will give us this decimal. What does this decimal represent? This is the power of 10 that gives us 8. So for example, if I do 10 to that power, the result should be 8, which is exactly what I get. Does everybody see that? Why 10? That's the base for the logarithm, right? Remember that when we write log, what base is on that logarithm that's there that we don't write down? 10. What if we wanted to take the natural log of 8? Well, you'll notice right below the button that says LOG is the button that says LN. So I can press that button, type in the number 8, close the parentheses, and press enter. And that's going to give me this decimal. What is this number representing? This is the power of E that gives me 8. Why is it the power of E? Because ln is log base E. So if I wanted to check that, I can do e to the answer, which gives me 8. Everybody okay there? What if I wanted to do log base 2 of 3? How do I do that on my calculator? Well, to do that, we're going to start by pressing the Math button. And then from the Math tab, which we're at automatically when we press the Math button, we're going to scroll down and look for the command that says log base. So press the Math button on your calculator. Scroll down till you find the command log base. Now, not everybody's calculator might have this. If you have an old calculator, this might not be included in your operating system. But most of you that have TI-84s or newer, it's probably there. So if you have one of the skinny calculators, for sure you got it. If you have a TI-84, I think you should have it. If you have one of the old 83s, the black ones, maybe not. Depending on the age of your 83, that might not be out there. But I think from seeing you guys' calculators, most of you guys have 84s or better. Did anybody not find the log base command on their calculator? Okay. So I'm going to press that log base button. And what this allows me to do then is I can type in a specific value for the base and type in a number for the argument. So if I wanted to do log base 2 of 3, it would look like this. And then I can just press enter. And then what does this number represent? This is the power of 2 that is equal to 3. So if I do 2 to that, and then if I just use this previous result and evaluate, I get 3. So what the logarithm is giving us is the exponent for an exponential equation, right? So log base 2 of 3 is saying, what power of 2 gives me 3? Well, 1.58 yada, 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 yada. Is everybody okay with that idea? Okay. You guys feel good about using the calculator to do stuff with the logs so far anyways? Okay. Good. So the next thing I want you guys to remember is was it yesterday? No, it was last time though. We said that exponential and logarithmic functions are inverses. Do you guys remember when we said this? Before we started talking about logarithms, we spent some time talking about inverses again so we could remember what that meant. So remember our definition that said that f and g are inverses if and only if f compose g of x is equal to g compose f of x, which is equal to x. Okay? So let's say that we have the function f of x, which is equal to b to the x, and g of x is the function log base b of x. What this is saying then is that f of g of x, when we write a composition like this, what that's saying is I'm going to take my value for g and I'm going to plug it in to my x. So that's saying we have b to the log base b of x. And this has to give me x, right? Because we know that exponential functions and logarithmic functions are inverses. That has to give me x. So what conclusion can I draw from this? is that exponent base b and log base b cancel each other out, leaving me only with the x. Everybody okay there? Similarly, since f and g are inverses, I also know that g compose f is equal to x. So what that means is I'm going to take my f and plug it in for the x in g. And since these two functions are inverses, I know that they equal x. So what conclusion can I draw from this? Well, log base b has to cancel exponent base b, leaving me with only x. So let's apply this to some simplification problems. Okay, so let's say we have 10 to the log of 4. What is the base on log 4? What is the base for the logarithm when I write just the word or the symbols log parenthesis 4? It's 10, right? Remember that this is the common logarithm. When I don't write a base for my logarithm, we understand that the base there is 10. Everybody's okay there? So I have 10 to the log 10 of 4. What do I know about the exponent base 10 and log base 10? What did we just learn in the previous? They cancel each other out. So what's the only thing that's left then? The 4. This is maybe the most important idea of this section, is this is how we're going to cancel out exponentials, or how we're going to cancel out logarithms. So let's say we have log base 5 of 25 to the x. What is the base on my logarithm? It's 5. What's the base on my exponential? 25. Can these two cancel out as they're currently written? No. However, is there a way for me to write 25 as some power of 5? Sure, right? What is it? 5 squared. So I can rewrite this as log base 5 of 5 squared to the x. So how do I simplify 5 squared to the x? Does anybody remember this rule for exponents? That's a time symbol. So that would just be 5 to the 2x, right? Because we're just going to multiply the 2 and the 5, right? So if I have an exponent of an exponent, the exponents just multiply. And now what can I do? So log base 5 and exponent base 5, the bases match. So now they can cancel. So what am I left with? 2x. What do you guys think? That's okay?
So the main thing about this is that you're trying to get the same number and that way you cancel each other out.
Yes, if the bases match, they can cancel.
Okay.
Justin,
I just have
you may. So let's say we wanted to find the inverse for this function. So remember, last time we met, we talked about how to find an inverse as well. Do you remember what that process was? It was 2 steps. We start by getting the x by itself, and then we swap the x and y variables. Everybody's okay with that? Kind of remember doing that? So in order to get the x by itself, what do we have to cancel out here in this problem? The 6. Great. What is the 6? It's an exponent base. Very good. So to cancel the exponent base of 6, what do we need to do to both sides? What's going to cancel the exponent base of 6? Log base 6. Very good. So I'm going to do log base 6 to both sides. So if I look at the right-hand side, what can happen? Log base 6 cancels with exponent base 6. And we're left with just the x. Notice at this point the x has been isolated. So my next step would be then to swap the x and y coordinates. And we're finished. Is everybody okay with that idea? Okay. Let's do another. Here we have the equation y equals the natural log of x plus 3. Remind me again, what is the base for the natural log? What was that? Not 10. So what is the base on the logarithm? ln? E. Very good. Everybody's okay with that? Remember that number E, 2.7, yada, yada, yada? Okay. So what are we going to have to do to both sides to cancel the natural log? We're going to use the exponent base E. So I'm going to write an e on both sides. And then the exponent is going to be y, and the other exponent will be the natural log of x plus 3. So notice how I wrote this e quite large and exaggerated. I want to emphasize that we're not multiplying both sides by e. We're making both sides exponential, where e is the base of the exponential, and the left-hand side is the exponent on the left-hand side, and the right-hand side is the exponent on the right-hand side. Everybody's okay with that? If I look at the right-hand side of this equation, what do you notice can happen? Exponent base e will cancel log base e. So what would we be left with on the right side? X plus 3. We'll continue trying to get the x by itself because we still have something going on there. What else do we need to do? Subtract 3. Now, a 3 and an e to the y are not like terms, so I can't subtract them directly, so I'll just write it right next to it. And now the x is by itself. So I can just swap the x and y coordinates. And there's my inverse. Is everybody okay on that? The last topic that we want to talk about today is graphing logarithmic functions. So my general form for a logarithmic function is this. Okay there? So these a, b, h, and k kind of do the same thing that we've seen over and over again, or the a, h, and k perform the same transformations we've seen over and over again, right? We've mentioned these like 3 or 4 times now this year. I'm not going to write them all down again because it's getting to be kind of overkill. What I want to do, though, is I want to think back about what we know about exponential functions, because logarithmic functions and exponential functions are inverses of each other. I can learn a lot about a logarithmic function from what I know about an exponential function. So remember, exponential functions have a special feature. Does anybody remember what that special feature is called? That dashed line that goes on the graph? Starts with an A. Well, it's actually 2 words, and one of them starts with an A. Yes. It's that line that you can't go past. Exactly right. It's called the horizontal asymptote. Does anybody remember how to find that? Okay. So the horizontal asymptote is y equals k. So if you remember, when we make an inverse, what are we really trading? The x and y coordinates, right? So if the exponential has a horizontal asymptote, what kind of asymptote would the logarithmic, its inverse, have? So if it's going left and right, when I switch the x and y's, which way is it going to be going? Up and down. So we'll call that a vertical asymptote. And the vertical asymptote equations start x equals, in the case of a logarithm, that's h. Okay. When we talked about a exponential function, what was the domain for all exponential functions? So it's negative infinity to positive infinity. Which coordinate is the domain talking about, the x or the y? The x. So if we're switching the x and y coordinates for our inverse, then the range for our logarithmic should be negative infinity to positive infinity. Is everybody okay with that, since the range is about the y's? Okay. Now, the range for an exponential had two cases. When the a was positive, we were doing k to positive infinity. And when the a was negative, we went negative infinity to k. Really, we're only going to deal with one of those two situations because of how we've defined our general form for logarithmic. If we were a little bit more abstract, we would have two situations here for our logarithmic, but it's beyond the scope of this class to do that. So here we're just going to have h to positive infinity. Which is kind of like our version here. Okay. The next thing we'll talk about is how to choose our x's. So the goal here, when we choose our x's, is to not get irrational values for y. We want to choose our x's so that the y values aren't going to be like some crazy looking decimals. The way to do that is to choose our x's in the following way. So this is how we'll choose our x's: b to the negative 2 plus h, b to the negative 1 plus h. Go ahead. Yeah. B to the 0 plus h, b to the 1 plus h, and b to the second plus h. Let's just plug one of these into our function just so I can demonstrate why these values of x are preferable. So let's look at b to the negative 2 plus h. So if I plug that into my general logarithmic function, I'm going to replace the x with b to the negative 2 plus h. And let's see what happens here. Notice that I have a plus h and a minus h. So those two can cancel each other out, right? So that leaves me with a times log base b of b to the negative 2. Notice that I have log base b of b to the negative 2. What can I say there? The log base b will cancel my exponent base b, and we'd be left with just a times negative 2 plus k. So the point of picking our x's in this way is they allow us to cancel the exponential and the logarithm to leave us just with a's and k's, basically, right? So if I continue filling out my table, those are the rest of my values for the y coordinates. So this should be relatively easy to remember because notice that the exponent on my x is just becoming the coefficient on my a. And my exponents are just counting up from -2 to +2, right? So that should be relatively easy to kind of keep track of that. So let's look at an example. So let's say I want to graph the function y equals log base 2 of x plus 3 plus 1. So the first thing I would do is I would just list my values for a, b, h, and k. What's my value for a? It's what? Log 2 isn't a number. That's an operation. I'd be saying like the number is square root symbol, right? 1, good. Because remember, this is what we're talking about. So if there's no coefficient out front, we know the number is 1. Good. What's the value for b? 2. What's the value for h? -3. And the value for k is +1. Okay. So the vertical asymptote in this situation is x equals what? Remember, it's x equals h. So in this case, that's x equals -3. What would the domain be in this situation? Remember, the domain is h to ∞. So that's -3 to ∞. And what's the range in this situation? It's always -∞ to ∞. Everybody's okay there? Now let's make an XY table. So I have b to the -2 plus h, b to the -1 plus h, b to the 0 plus h, b to the first plus h, and b to the second plus h. If I go and I type these into my calculator, I would get -2.75. This would be -2.5. This would be -2. This would be -1. This would be +1. And then for the y coordinates, I'll do -2 times a plus k, -1 times a plus k, 0 times a plus k, 1 times a plus k, and 2 times a plus k. If I go and I evaluate those, I get -1, 0, 1, 2, 3. And if I draw my graph then, I'll start by drawing in my vertical asymptote. And then I'll plot my points. Hold on for 1 second, guys. So there's my graph. you guys do have an assignment. I've posted that assignment to the Power School calendar. You'll have to check or have to print your own, but it's there. Worksheet 4. Thank you.